Hello everyone. Welcome back to ILTA Physics problem solving session. Today we're going to work on some problems involving impulse and momentum. Impulse is defined as the total amount of force applied when objects collide, while momentum is a physical quantity that a moving object possesses. You can also think of momentum as mass in motion. The relationship between impulse and momentum exists because the force generated by an impact creates acceleration of an object, which then results in motion. If you feel like you're lacking a physical understanding of this concept, I recommend studying my theoretical lectures first before coming back to these practice problems. The problems we'll solve today range from simple ones, where we calculate impulse and momentum using basic formulas, to more complex scenarios involving the relationship between the impulse generated during a collision and the resulting change in an object's momentum. All right, let's start with a quick review of the theoretical concepts. Up until now, we've mostly focused on the motion of a single object moving along a straight or circular path. From now on, we're going to analyze the motion of objects when two or more of them run into each other or collide. When two objects collide, we define the overall effect of the force as impulse. Now, when I say total force, keep in mind that even though collisions happen in a split second, they are technically events that occur over a very small time interval. Since the amount of force acting during that tiny window isn't constant, we define an average force for that duration. We then calculate impulse by multiplying this average force by the collision time. The unit for impulse is the Newton second. These collisions apply force to an object, which then changes its motion. We've already spent a lot of time analyzing motion kinematically using parameters like velocity and acceleration. However, an essential concept for dealing with motion from a kinetics perspective is momentum. Momentum is defined as a physical quantity that a moving object has, and it's often described as the mass of a moving substance. That might sound a bit philosophical, but simply put, you can think of it as a measure of how difficult it is to stop a moving object. In other words, the heavier and faster an object is, the greater its momentum. Therefore, the harder it is to stop. Mathematically, the momentum of a moving object is calculated as the product of its mass and velocity. The key takeaway here is that when objects collide, the impulse is equal to the change in momentum. That is, the amount the momentum increases or decreases. This is known as the impulse-momentum theorem. Mathematically, we can state that impulse equals the change in momentum. Since the mass of an object generally stays the same, the change in momentum can be calculated by looking at the change in velocity before and after the collision. Specifically, it's the difference between the final velocity and the initial velocity. Most of the problems we're solving today use this impulse-momentum theorem. One last thing to mention. Newton's second law of motion, which we all know as F equals ma, can actually be explained more precisely using the momentum we define today. According to the impulse-momentum theorem, the impulse and the change in momentum are equal. Through a bit of math, we can see that the force applied during a collision is equal to the change in momentum divided by the collision time interval. Since momentum is mass times velocity, and the change in velocity divided by the time interval is acceleration, Newton's second law can be rearranged like this. If these theoretical concepts don't quite make sense to you yet, please go back and watch the related lectures to make sure you have a solid grasp of the material before jumping into the problems. Remember, solving problems without a physical understanding of the concepts won't help you much on the actual exam. All right, let's dive into the problems. Problem number 2 describes a situation where two students are rolling bowling balls of different weights. It asks which bowling ball has more momentum. As we discussed, momentum is a physical quantity often described as mass in motion and the formula is mass times velocity. For the first ball, we're given the velocity and the mass, so using the formula, the momentum comes out to 32.4 kilogram meters per second. If we call the velocity of the second ball v2, its momentum is also calculated as mass times velocity. For the second ball to have more momentum than the first, the relationship shows us that its velocity must be greater than 5.06 meters per second. As you can see from the results, since the second ball is heavier, it can have more momentum even at a lower speed. Problem number 5 describes a scenario where a student throws a snowball at a wall and it sticks. If the collision between the snowball and the wall lasted 0.15 seconds, what was the average force applied to the wall? Whenever you see a problem where objects collide like this, the first things that should pop into your mind are impulse and momentum. First, let's think about the average force mentioned in the problem. If we plot the force the snowball exerts on the wall over time, it looks like the graph shown below. As you can see, the force starts small when they first touch, peaks, and then gradually drops back down. The important thing to note is that the force is not constant, even during that very short collision time. This is why we define an average force, which is the total impulse divided by the collision time. That's exactly why the problem asks for the average force. Let's first calculate the change in momentum for the moving snowball. Since momentum is mass times velocity, the change in momentum is the mass multiplied by the difference between the final velocity and the initial velocity. The crucial detail here is the snowball's final velocity. The problem states that the snowball stuck to the wall. This means it stopped moving forward, so its final velocity is 0. Make sure to keep practicing how to find these hidden conditions within the problem descriptions. So, using the formula, the change in momentum is minus 0.9 kilogram meters per second. According to the impulse momentum theorem, the change in the snowball's momentum is equal to the impulse applied by the wall. Using the formula, the average force applied to the wall is the change in momentum divided by the collision time, which equals minus 6 newtons. In this calculation, the negative sign simply means that the direction of the force is opposite to the direction of motion. In other words, you can think of it as a force acting in the opposite direction of the snowball's flight, which causes the snowball to come to a stop. Problem number 8 involves a collision between two billiard balls of the same weight. The first billiard ball hits a second one that was at rest. After the collision, the first ball stops right there, and the second ball moves forward. The collision lasted for 250 milliseconds. The problem asks for the average force exerted on both the first and second billiard balls. For collision problems like this, a great way to start is by drawing a before and after diagram just like the one on the right. Before the collision, the first ball is moving to the right toward the stationary second ball. During the collision, which lasts 250 milliseconds, each ball exerts an equal amount of force on the other. This is explained by Newton's third law, the law of action and reaction. After the collision, the first ball stops, and the second ball moves to the right. For collision problems, please remember once again that coming to a stop means the velocity is 0. Alright, let's first calculate the change in momentum for the first ball. Using the same method as before, since the first ball stopped after the collision, its final velocity is 0. So, based on the formula, the change in momentum is minus 2.02 kilogram meters per second. And by the impulse momentum theorem, the average force on the first ball is the change in momentum divided by the time interval, which gives us minus 8.08 newtons. Again, the negative sign indicates that the force is acting to the left, opposite to the ball's original direction, as shown in the diagram. So, what is the average force exerted on the second ball? We can easily solve this by looking at the moment of collision through Newton's third law. According to the law of action and reaction, the force exerted on the second ball is exactly equal in magnitude but opposite in direction to the force exerted on the first ball. The minus sign here again shows that the two forces are in opposite directions. Therefore, the average force on the second ball is the same magnitude but in the opposite direction, 8.08 newtons. Problem 16 is about a collision involving a rope used to stop a rock climber from falling. The problem asks, if an 80-kilogram object falls from a height of 4.8 meters and the force that stops it is 11 kilonewtons, how much time does it take to come to a stop? At first glance, catching a falling object with a rope might not seem like a collision. But in physics, since a force is being applied to stop a falling object upward, it can be treated with the same concepts. Please take a moment to read the situation described in the problem carefully and make sure you understand it. Once you've got it, the solution process is very similar to the previous problems. One extra step we need is to find the final velocity of the object falling from 4.8 meters. Using the relationship between the final and initial velocity for free-falling objects, the velocity after falling 4.8 meters is 9.7 meters per second. Now that we have the velocity, the change in momentum is calculated by the formula as minus 776 kilogram meters per second. Again, using the impulse momentum theorem, if the average force provided is 11 kilonewtons, we can find that the time it takes for the object to stop is 0.07 seconds. That's it for today's lecture. Great job, everyone. I'll see you in the next session.